So welcome back to the Energy Efficiency in Buildings theme. I'm Dave Jenkins from Heriot Watts, for those who weren't here in the last session. So we've got 4 more talks to finish off with today. Usual kind of rules, so you get a bit of a 1-minute warning when you get to 9 minutes, and then you've got a few minutes, well, you've got a minute to wrap up, and then hopefully a few minutes for questions after that. And Daniel at the front will give you a 1-minute warning when you get to that point. So first up, we have Maza Saifika from Heriot Watt University, and she's going to be talking about occupancy characterization in non-domestic dynamic building simulation. So over to you, Maza, and hopefully you can find your slides on the, if you flick through to the next.
Thank you. Hi everyone, my name is Maza and I'm a PhD student at Heriot Watt University. My research is focused on the role of occupancy in non-residential buildings performance simulation. And in this presentation, I'm specifically looking at energy results and performance gap. So occupancy refers to the presence and numbers of occupants in a building or a space. And it has an effect on building energy usage because occupants release heat through their body, and that can affect the internal heat gains in the building, which can affect the heating and cooling demand of the building. And also when people are in the building, they use electrical appliances and lighting, which contributes to the energy consumption as well as the internal heat gains. Also, ventilation demands are affected by occupancy because, especially when demand-controlled ventilation is used or in spaces where natural ventilation is used. So it's really important to look at occupancy in building energy use as well as in building performance simulation, and to look at its effects on energy results. The common way of representing occupancy in BPS, or building performance simulation, is using standard profiles such as ASHRAE 90.1 or NCM here in the UK. But as you can see, these profiles can be a bit simplistic and sometimes overestimate or underestimate occupancy levels. In these 2 examples, which are taken from studies in single occupancy offices, you can see that there is quite a significant difference between occupancy levels in a database profile versus the ASHRAE 90.1 profile. So to address this, studies are looking at representing occupancy in other ways, including database deterministic models or stochastic models. And some of these studies are looking into how these improved forms of occupancy inputs impact performance and energy performance results. However, most of these studies are focused on office buildings and specifically single occupancy offices. But it's also important to look into other types of buildings, such as public buildings or academic buildings, where larger numbers of occupants use the building and therefore probably have a bigger impact on the simulation results. Also, these types of buildings usually see larger variations of occupancy throughout the seasons or throughout the day. So it would be interesting to look at the impacts of occupancy on the simulation results for these types of buildings as well, which is what is a part of my research. So in this presentation, I will be presenting my results for 2 case study buildings, which are at Heriot Watt University campus here in Edinburgh. The first one is the library building, and I had access to 8 months of occupancy data for this building, which was collected by the swipe card entrance. And also I had the manual count data for the same period, which were counted in evening hours and late night hours. The second case study is the postgraduate center building, also at Harriet-Watt. For this building, I had an entire year of half-hourly occupancy data, which was collected using an IR beam sensor installed at the entrance of the building. Also, I had access to half-hourly electricity and gas meter data, which helped me study the effects of occupancy on the performance gap as well. In order to provide some comparison ground and highlight the impact of occupancy input, I've compared the results to the results of using improved weather data as well, because weather data is also another input that's considered to be important in the results of a simulation. So, and the metric for comparison that I've used is CVRMSE. So for the library building, as you can see, after processing the data set and eliminating the errors, I have distributed the building level data in between two space types, office spaces and communal spaces. This was done using the capacity of each space type and the operation hours. And after using a clustering algorithm, I ended up with different sets of profiles for these two space types, which are for weekends and weekdays during academic term and the break period. As you can see, the NCM profiles and the data-based ones are rather different. Also, in order for the electrical equipment profiles to match occupancy of each scenario, I have modified the equipment, the NCM equipment profiles based on the modified occupancy profiles for this building. For the postgraduate center, after processing the data and eliminating the errors, because I had the entire year of data, I didn't need separate profiles. I just distributed the data between different space types, including classes, offices, cafe, lecture theater, etc. For the electrical equipment in this building and lighting, I've used the meter data and used a clustering algorithm to create 3 sets of profiles for different periods of the year, and I've used these profiles in simulation to get better results. So if we calculate the numbers of occupants inside the building for the library building using occupancy density values and occupancy profiles provided by NCM, we end up with a profile that's like an M-shaped thing. So as you can see, when we compare these values to the database values, we can see quite a big difference for even for term time weekdays. But when we move to the break period, break weekdays here, break weekends, and weekends over the academic term, we can see that the difference even increases. For the postgraduate center, the trend is a bit different. As you can see here, the NCM profile underestimates occupancy numbers over the peak period for weekdays in academic term, but underestimates and overestimates the values for the break period and the weekends during term time. So let's see how these differences translate in energy results. For the library building, the natural gas consumption when we use actual occupancy profiles increases by quite a lot, but when we use actual weather data, it just increases a bit. The same goes for electrical equipment, electricity consumption, and HVAC electricity consumption, with the difference that actual occupancy profiles decrease the energy consumption. So if we compare the results using the metric for comparison, which is CVRMSE, we can see that using actual occupancy profiles has led to these differences, while using actual weather data has led to much smaller differences. For the postgraduate center, because I had the meter data available, I was able to study the performance gap, the impact of occupancy on the performance gap. And as I've shown in this table, using database occupancy profiles has led to 9% and around 12% improvement of performance gap for gas consumption and electricity consumption, which is more significant compared to the impact of weather data. So these results highlight that we have to consider occupancy inputs in building performance simulation of these building types as well, and not just overlook occupancy inputs and use standardized values. Thank you very much for your attention.
Okay, any questions from the floor? And if there are, we have a microphone that we need to use this time. While you're thinking, oh yeah, one question there. I think it might need switching on.
Hello, it's working. Great presentation, well done. I just wanted to check what the next step is. So I think that's really important to demonstrate that occupancy is valid for building simulations or modeling. How do you raise awareness of this beyond this room?
Well, there is good amount of awareness about occupancy profiles in building performance simulation. Actually, there are two, I think, IEA annexes focused on occupant behavior representation in general in building performance simulation. But occupancy has been a bit overlooked, but people are looking into it. And for me, for my research, the next steps are probably, I'm looking into finding more case study buildings to maybe be able to generalize some of the conclusions, because limited numbers of case studies really don't produce reliable conclusions. Okay, here we go.
Okay, so maybe a technique problem. So for the NCM like result, how did you do that? It's based on simulation or?
Sorry, I didn't get.
Could you go back to the slides with the comparison between? Yes, maybe this one.
Okay.
Yeah, you have the NCM.
Yeah.
It's based on simulation.
Well, you know, NCM profiles and density values are provided in the guidelines.
Oh, the Asian
so
guideline.
you have different space types and the square meter of each space type. You have the occupancy density, and you have the diversity factor for each time step. So you can easily calculate the numbers in each space. And then add up for the building level occupancy.
Okay, so it can be easily calculated, or based on simulation you can get it?
No, just by
okay.
MATLAB.
Okay.
But
yes.
no, not simulation.
Okay, thanks a lot.
Sure.
Maybe one kind of follow-up question based on the first question in some ways. How would you, the kind of method you're developing, how would you maybe sell that to a building user or building energy manager or facilities manager? Because as you say, there's lots of this work, there's quite good awareness of this type of work in literature, in the sort of research literature, but how would you sell it to an end user as a good thing to do? This is actually how you should model your building.
Well, first of all, the impact on the performance gap is quite significant specifically because most energy modelers have this in their mind that occupancy inputs just put in a standard ASHRAE or NCM value, or for each country their own specific standard ones. But we can show through these case studies that that's not true, even compared to the weather data, which is something that most people think is very important, especially for like heating demand, which is quite important in the UK. We can see that occupancy in these buildings, where the number of occupants are a lot, even though they don't have access to building services. And also, I didn't use demand. These buildings didn't have demand-controlled ventilation, and we didn't even consider that in simulation. So if you even have a building with demand-controlled ventilation, these effects will be much, much larger. So I think that's an important thing if you want to minimize the performance gap, which is, I think, the goal of every modeler. So yeah, I think I hope I answered.
Yeah, you did. Yeah. Okay. Thanks very much, Mazza. Next up, we have Robin Talbot from Brighton University, which isn't in Scotland, but you are very, very welcome. And I think Robin's going to talk about the different heating strategies in church buildings, which I think, as a building type to simulate, that's got to be the most difficult possible building I can think of. So I'm interested to see what you've come up with. So Robin, over to you.
Thanks very much. Yes, carrying on the theme of non-domestic buildings, I've been funded through an initiative, a Centre for Doctoral Training called CHA, which funds heritage science studies. So I'm at the end of my PhD. I'm just writing things up, so I've got a lot to say, so I'll try and fit it in 10 minutes. But generally, why would net zero be difficult for individual churches? The decision makers in local parish churches are a collection of people who might be professionals in their own respective fields, but they're not energy managers. They don't know about building services. So their understanding of what the national church has said about net zero might be slightly limited, and they might not understand it. So just going through some of the headlines that you might see coming out about net zero, and why it might be a very confusing topic for somebody who doesn't study it. It's a dangerous trap, according to some, but it is a solution for the energy crisis. People saying in an article it's a quasi-religious pursuit of the government with quack science. So it's a whole mishmash of theories, and Ed Miliband saying we should have done things much sooner and we wouldn't have been exposed to this energy crisis. Somebody during the COP26 saying global warming is not a problem, and carbon dioxide obviously helps plants. No issues here. Also that it's just an elite thing, that the poor are going to suffer because of the elite's obsession about net zero. Obviously we need to make vast changes to achieve net zero, so it's a terribly frightening prospect. And then just on churches in general, this was quite recent, we're going to force poor parishioners to shiver in their churches because they'll have to turn their heating off because smaller parishes can't meet these obligations, and perhaps the church doesn't have enough money in the first place to do this. One last thing, it's perhaps unlawful was the recent headline, so there's loads of things going on. This is the International Energy Agency's roadmap to net zero by 2050. So the green ones are about buildings, so I'll just highlight a few of them. All new buildings are zero carbon ready by 2030. 2035, most appliances and cooling systems sold are best in class. 2040, 50% of existing buildings retrofitted to zero carbon ready levels. 2045, 50% of heating demand met by heat pumps, and then 85% of buildings are zero carbon ready by 2050. So that's a lot of work to do, and the churches are now saying we'll do everything to get to net zero by 2030. So rather than have 28 years, they'd rather have 8 years. Now, why on earth would you be choosing less time to make these changes? So What the recent information from the Church of England in their 2020 emissions data, in a sample, it's quite clear that churches use a lot of energy for heating their buildings. Lighting and other uses are less prevalent, but it's quite easy to change the lighting to LED. So, but the heating problem remains a big issue, and we're really not going to be able to change the fabric and the structure of the churches. We're not going to be changing the look of them because they're historic, they're listed. We want to preserve them for future generations. So it's going to be about changing the heating efficiency and about the strategy. However, the recent data suggested that 60 out of the 16,000 Church of England churches, 80% of the emissions come from 33% of the building stock. So that's about 5,000 churches are the biggest emitters. It's likely to be the cathedrals and large churches that are heavily experience heavy usage rather than the small ones. So it leaves the smaller, less used buildings could make changes much easier than these large busy ones, and also be quite substantially cheaper to make those. The structure of my PhD has other elements, but I'm mainly focusing on these two. But some of the conclusions from earlier is that we're imposing our expectations upon these old buildings. We can't really expect them to be comfortable all the time. If we do change the strategy, what's it going to affect? Well, we've had a lot of these artifacts, artworks in buildings for a long period of time, even before they were heated. And then we put heating systems in and probably damaged most of them in the process, and you can't reverse that damage. If they're generally in a good state of conservation, you should just leave them to be. You can't create an ideal climate now, so don't attempt to do that. So even if you change the heating system and the strategy, you're probably not going to drastically impact many of the items that are contained within the church. We're really looking for these two strategies together: low temperature heating for extended periods of time and a radiant system. Rapid increases in air temperature for short periods is what we've been trying to do for years, mainly without much success, because churches are generally cold despite all the energy we fling into them in the heating. So it's looking at heating the people, and the national churches have said that. Don't heat your building fabric, heat the people. And really, I know when you go into some churches, they give you the hymn book and the Bible at the door, and I thought maybe in the future we could pick up our heated cushion and take it to our seat and find our own place to sit and then turn it on. These are a particular brand, and they can be battery powered. Some churches have fixed pews, some have always had movable seating like this, but we're really looking for this type of system where people can be heated wherever they're located in the building, rather than trying to uniformly heat it to some temperature that's mainly unachievable. We use the projected mean vote scale for this study. -3 is cold. When you calculate these figures, they're often below -3, which in Scottish terms could be absolutely Baltic, and that might be the relevant term. But so I've used Design Builder to simulate what changes could be made, and I have monitored a church in Shoreham by Sea, which is in West Sussex, for a year, and I've got the data. And this is the one day in 4th of January. The church's comfort level is below cold, despite the heating being on. This was just before the pandemic, so the church was in regular usage. Along the top are the various different types of localized heating systems you could use: heated cushions, radiant high temperature radiant panels, low temperature ones which would be attached to the pew in front of the person, and then I've modelled these at different occupancy levels so that the half the equipment is on and then the full output of the equipment is on. Now, what I must say is I do not have temperature. The first three, there's 2 at 20 degrees. The church has never been monitored at 20 degrees. It's often lower. So this line, the brown dotted line, is other models. And it shows that when I apply these scenarios to the actual church data, it's fairly, it aligns quite well with the simulation models. So if you were achieving 14 degrees with another heating system like either traditional radiators or a heat pump. If you had a heated cushion as well, you could almost get to what is considered by SIBSE as a comfort level at 0. And most people would be okay with that. It still requires a bit of thinking. Churches that have got fixed pews aren't really going to be used for much else unless you remove those pews, and there is a movement to take the pews out so the building is more flexible. If you're doing different activities, sports, dancing, exercise classes, or some kind of standing around doing something, these are different activity levels, and what is the result of doing those in a historic church? There has been a tendency for churches to think we must have underfloor heating, but very old historic churches, hundreds of years old, tend to have graves and flagstones with inscriptions on the floor, so we're not going to be able to rip up these floors and install underfloor heating, and it's often not that successful in large volume buildings because you're still trying to heat the building fabric to a uniform temperature. So if you think of this, if you take the pews out, this has got high temperature radiant panels that work around 1,000 degrees. That covers quite a large floor space, and you could do a different activity there if the pews were not there. So I've modelled some, or calculated different activity levels and what that would mean in terms of comfort. The yellow band is where most people would find comfort. So in a non-heated church on the far left, if you were just sitting in it, it's dreadfully uncomfortable. But if you're doing some different activities, at 3 minutes, which is light dancing, you would maybe find that was fine. As you use the radiant system to add radiant energy into the building, you're still okay with the comfort level. Certain output levels might push people into being overheated, and then the gas boiler scenario running four times a day has a mix of comfort levels. I'm generally looking to help the church to make decisions and the local decision makers. So it's attempting to harmonise this guidance with what the church is saying. They've got an awful lot of information to read for local parishes. It's a suite of documents. But basically it's come down, it looked like it would be a very complex set of variables, but actually it's really only, are you using your building a lot, or are you using your building a lot, or are you using it very infrequently? Some churches are only used once a month at most. So these are the basis of the decisions, and net zero targets are a really good opportunity for the churches to readdress what is comfort and how you're going to achieve that. They are kind of fixed in their mind, we must have a gas boiler or we must have an oil boiler, and this is an opportunity to change that. It does come down to usage. They might be doing additional wider building works, reorganising the church, removing things, reorientating where they do their services. That might come into it, and they might want to make larger scale changes. It's not possible to find one solution, but the smaller churches are likely to change much easier than the larger churches, in my opinion. And if you can, it does give the opportunity to provide this low-level heat in the building fabric, which can be achieved by heat pumps rather than using traditional fossil-fueled boilers. So it's a really good opportunity for churches to make these changes, and that's all I'll say. Thank you very much.
Thank you very much. And questions from the floor? Again, with microphone if required. Got a couple. Thanks, Daniel. It does remind me that SIBSE Guide A, for those of you that use such things, does have a category of moderate dancing for the amount of internal heat gains generated by people, which always makes me laugh.
That was really interesting. I was just wondering if you'd done any sort of economic analysis about sort of energy costs.
Yes.
With the original heating system and then the different options afterwards.
I've not been so focused on the cost of the heating system. My supervisor from the Church of England, the Diocese of Chichester, has given me data on the indicative costs for various installations that they know about. So there's a never-ending stream of things to look at the end of your PhD, and it's just another thing I've got to look at. I have attached values to the consumption data out of the simulations, because it provides what is to be expected gas consumption, etc., electricity. But I did that before the pandemic, so it does look cost-effective. Electricity is generally more expensive than gas. That's the general problem with changing to electrical systems. But if you're trying to reduce the temperature in the building to a lower level and then using much more energy efficient radiant or localized systems, it's likely to be very much cheaper for churches who already have massive cost burden for trying to heat the building, so it's probably quite a saving.
Is there any other questions on the floor? Yep.
Yeah, just in terms of the churches, so in Scotland there's funding available for businesses up to £100,000 grant funding, and a lot of churches have availed of that.
Yes.
Having looked at some of the bigger spaces, sort of warehouses and things in Glasgow, and radiant heating and CHP boilers are recommended sometimes, and is there a mix between the key drivers, say, for the church themselves, so the board or the people that are looking after the church, to say, well, why should I invest? Maybe beyond just the financial aspect of it, in terms of creating, say, occupancy, bringing people into the church, and it becomes more of a community centre, but it also addresses fuel poverty, because if you're sat at home freezing, you can go to this community space, have a sense of well-being, which is a local church, and I'm sure people that running those churches be interested in getting the congregation or people, the community, back in again. So I guess have you seen that thinking coming across in the discussions you've had?
Yes. Well, in 2017, the Taylor Review looked at English churches and cathedrals and what the future would be like, because there's about 5,000 churches that have to have financial support every year because they're unsustainable, and the government and the Church of England wants to move to a different model where churches are self-sustaining, and the only way that's going to happen is if they can generate income. And that's one of the drivers for this project, because the churches are so cold and uncomfortable, you cannot really viably hire out a facility that's so uncomfortable to people. They won't pay. And so it's trying to make individual parishes see that there is a future, and it doesn't have to be always asking for money, having a fund going. It can be self-sustaining through using the building in a better way for the community.
Thank you.
Any final, very quick questions at all? No? Okay, thank you very much.
Thank you very much.
Okay, next up we have Leslie Thompson from Heriot-Watt University. And Leslie's going to talk about the use of real energy consumption data in characterising residential energy demand.
Slightly change the title to make it even more of a mouthful than that. So the title of this presentation is the use of real energy consumption data in evaluating energy performance and characterising residential energy demand. So I'll begin with talking about the current approach to energy performance evaluation of residential buildings in the UK and its limitations, and then alternative approaches to assessing energy performance using real energy consumption data, and then the use of high resolution data to characterise residential energy demand and performance, and then finally the role of consumers and potential future metrics. So the Energy Performance Certificate, EPC, is used to assess the energy performance of domestic buildings in the UK, and a calculation engine is used to generate a value for modelled annual energy use and annual CO2 emissions, and these are translated onto a scale to give an energy efficiency rating and an environmental impact rating for a property. And the underlying calculations are steady state, and they make simplifications to the thermodynamic processes, and there's also standard assumptions made about use and occupancy. So this standardised approach allows for inter-building comparison, and the EPC also gives recommended measures for technologies that could be implemented to improve the energy efficiency of the property, and gives indicative costs and typical savings of these over 3 years. So I've said that this standardised approach allows for inter-building comparison. but this kind of modelled approach does have some limitations. So because the true occupancy of the property isn't taken into account, there can be a difference between the modelled energy demand from the EPC and the actual annual energy demand that's reflected in utility bills, called the performance gap. We've heard about that a few times already. And research has shown that that can be worse for older properties. And I showed in the previous slide that on the EPC it gives indications of the cost savings that could be made by installing energy efficiency measures in a property. So the implication of the performance gap is that if the real energy demand is less than that modelled, then there could be an overestimate of the energy and CO2 savings that can be made through retrofit, and the energy efficiency measures themselves could be less cost effective than predicted. And this could be quite significant if we consider the age of the building stock in the UK. So the graph on the right shows that more than 50% of properties in the UK were built pre-1965, which is more than 15 million dwellings, and a high proportion of those are expected to still be in use in 2050. So that's some of the limitations of the sort of modelled approach to energy performance evaluation, but we do have access to measured energy consumption data, whether that's through sort of quarterly or annual meter readings or from smart meters. So alternatively, we could use measured or real energy consumption data to evaluate energy performance. And in Sweden, Germany and Poland, measured annual energy consumption data can all be used to form the basis of an EPC. So we might think this kind of solves the problem because there should be no performance gap, but there are still some limitations to that approach. So, for example, it's difficult to compare buildings between one another because occupancy characteristics are different between properties. And some types of properties, like holiday homes, might have incomplete information. In research, there's also some schemes being proposed to use annual energy consumption to evaluate energy performance. So the first here is the EU-funded Extendo project, which has proposed a measured energy performance indicator to be added to an EPC. And the way that's calculated enables comparison between buildings. And a methodology for a domestic operational rating was published by a group from Loughborough and Leicester. So all the approaches so far to evaluate energy performance that I've mentioned, they're all focused on annual energy consumption. But going forward, there's predicted to be sort of wider electrification of the energy system, including for heat, with more generation from renewables that can be intermittent. And the graph on the right shows a possible scenario of uptake of heat pumps in UK residential buildings until 2050. So with greater electricity demand and more supply from intermittent renewables, supply-demand management will become quite important. And the graph on the bottom left just illustrates this. It might be slightly exaggerated, but it's just to illustrate the point. So you've got onshore wind supply in grey, and then electricity demand in blue. And quite frequently the demand exceeds the supply. So this could become a reality with, electrification of heat in other sectors such as transport. So with that in mind, are there alternative ways to evaluate energy performance that are more fitting for a future energy system? And by that I mean looking at high resolution energy data and transient or temporally varying properties of energy demand profiles, rather than just considering performance in terms of annual energy consumption. So what kind of data do we have to explore this? Well, there's quite a lot of high resolution energy demand data that's been collected in the UK. So there's quite a lot on this graph, but these are the data sets that are available. The y-axis has data set temporal resolution and the project timeline on the x-axis. And it's coloured by the order of magnitude of the number of sites. And it shows that there's gas and electricity data available. So it's quite a wide range of data sets. Some are very high resolution, down to 1 second for order of magnitude of number of sites of hundreds. So quite a lot of data sets available, all sort of different applications depending on what's contained within the data set. But a lot do have contextual data associated to them. So that could be information on the physical properties of the dwelling, the occupant characteristics, appliance use, internal temperatures and weather that can add further meaning to the data sets. So I've said that we'd like to kind of analyse energy demand data at a higher resolution, and there's quite a lot of data sets available to do that. So what techniques are available? There's quite a lot. There's a few kind of mentioned on this slide. Clustering is quite a popular technique in this area, which is a data-driven machine learning technique that clusters energy demand profiles into an appropriate number of clusters for the data set. And there's an example here on the bottom left, so it shows natural gas profiles divided into 4 clusters with the representative profile for each shown in black. This is for natural gas, but a lot of the literature in this area is focused on electrical non-heating loads. So the different ways that the data could be dissected for clustering, so you could look at weekdays, weekends, or different seasons, or potentially different building archetypes. Principal component analysis is another example, so there's a reference given here in the bottom right, and regression as well is used commonly, so data sets that have some contextual data associated to them, whether that's to do with the building or the occupant characteristics. Regression's been used to look at to understand the variables that are driving the variability across load profiles. So there's a lot of data analysis techniques that we can use to analyse high resolution energy data. Some of them I mentioned on the previous slides, and these can kind of yield interesting insights into energy demand profiles, but changes to the energy system are going to affect most householders, and we've seen recently about energy suppliers looking to incentivise consumers to be more flexible in their energy use. And I talked about the potential for greater electricity demand and the importance of supply-demand management. So it's possible that we're going to have to become more engaged in our energy practices, and so it'd be interesting to find out from consumers, what information would they like to know about their energy demand that could be extracted from high-resolution profiles that could help them to become more informed about their energy use practices. And a lot of us have sort of smart meters ticking away in the background collecting half-hourly readings, but what could be gleaned from that type of data that's not just given an up-to-date cost, but perhaps there's new metrics that could be defined to evaluate energy performance, and some of those are listed in the bottom of the slide. So in conclusion, EPC is fit for its purpose, but are the purpose and requirements of energy performance evaluation changing? Could we have new ways to usefully evaluate energy performance based on high resolution energy demand data? And it could be beneficial to have buy-in from consumers to promote greater awareness of energy use practices, and we should look to metrics or indicators that go beyond annual energy consumption that are more fit for purpose for a future energy system. Okay.
Great, thanks Leslie. And once again, any questions on the floor?
Sorry to hold the mic.
That's right.
This is being recorded, so I've got to be careful what I say. But, yeah, I think it's really good that EPCs are looked at. For example, I live in an 1840 tenement building in Stirling.
Yeah.
It's got an EPC rating of C, but I still freeze in winter. So that is the recommended level that we're going to be going to in Scotland, but I think there's work to be done, and this work is good at highlighting that. So,
yeah.
what do you think could be the next step for this? Any plan? Great plan.
I think there's, as Dave mentioned earlier, there's a lot of work looking at EPCs, because I suppose the kind of problem with EPCs from our perspective is that it's a tick box exercise really. So you kind of have to have it if you're selling your property or if you're renting somewhere out, and it's almost something that you just take, and then you have to pay for it, and that's fine, and then you kind of don't really look at it again. And there's obviously these kind of recommendations that are made, but if someone's kind of telling you that it's going to cost £4,000 to install solid wall insulation, it's going to save you £300 a year, then kind of thinking, well, why would I do that? So there has to be a lot more kind of buy-in from homeowners and things to actually buy into what the what the recommendations are, and there's potential for more kind of modern metrics that could be added to EPCs, but a lot of those are more focused on kind of annual consumption, which gives you kind of an indication, but it doesn't really tell you what's happening throughout the year. So this work is more kind of focused on looking at the higher resolution data. So EPCs are more kind of focused on the annual consumption, but this would be a bit more looking at higher resolution. So there's talk about having things like online EPCs. So if you go on to, I think they have in England and Wales, they have a more online database. So maybe you could go on and see maybe some more live data or something. You could compare your energy consumption patterns with a similar property, things like that. So just having a lot more awareness of sort of your energy practices compared to others. But that's kind of what I'm saying, you know, all these changes, they do require buy-in from consumers. You can't really just impose changes on people and expect them to accept it and not explain why these changes have to be made.
Yeah, I actually like the third conclusion there about there could be beneficial. It could be beneficial to have buy-in from consumers.
Yeah.
So, what sort of benefit do you think consumers might get from that?
Well,
Aside
sorry. Well, I think just like I was saying, you know, just having, you know, people were kind of saying everyone needs to have a smart meter, and it's just your energy company just says we have to come and install this smart meter, but it's going to save you money, but so it doesn't really save me money by actually having it sitting there ticking away. I mean, it might, I don't know, might kind of influence what you're spending, but it's not really, just having one installed isn't going to, you know. So having just a lot more understanding of why we're having to have smart meters and, you know, the kind of way the future energy system is going. But like I say, you can't kind of impose things on people and just, you know, because a lot of these technologies that people are talking about, they're expensive. So you can't just say to, you know, we were talking earlier about this rollout of heat pumps and things like that, but I mean, if someone's going to spend £10,000 on a heat pump, you know, that's a very good reason for doing that. So just sort of taking people with you rather than imposing things on people and having buy-in from consumers.
Thank you.
Any further questions?
Hi, sorry, I don't know, I hope I'm not repeating myself, but I was going to ask, I mean, how does this help in improving energy efficiency in the homes?
Well, I suppose if people are more aware of their practices, so one thing that I'm thinking about is, say you live in a solid-walled flat, and you can look at your energy performance in a higher resolution scale, and you can compare that to others. Then that might kind of influence you to think about, okay, right, so my property looks like this. This is sort of the average for this similar type of property. Okay. You know, kind of benchmarking yours against others. They do that quite a lot in other countries. There's schemes in the States and also in Australia where they have sort of benchmarking schemes. Again, they're all based on annual consumption, so people can kind of put in information about their home and they can sort of benchmark that to an average of a similar type of property. So I guess you could kind of look at your sort of energy demand profiles, what your energy consumption looks like, and sort of benchmark that against other similar properties. It could potentially influence you to maybe change your behaviours, and maybe there's technologies that you could install that other people have, things like that.
That's not enforceable, really, is it?
No, well, exactly. Not yet, anyway.
A follow-on question, just what you said. Yeah.
The application maybe for real estate, for renters or for the commercial property market or domestic people purchasing homes to have a cost of living over a certain time period based on 1, 2, 3 occupants.
Yeah, exactly. So that's the thing about sort of looking at the real data is obviously it's influenced by the occupants that are living in it, so you have to be sort of quite careful with making sort of generalised comparisons between, the building might be the same but the occupants living in it, but you could subdivide it by the number of people and things like that.
There is a measured operational rating being proposed at kind of EPC land at the moment. That's one of the metrics being tested out, which can be kind of normalised on occupancy and weather. So you can, it's very difficult to standardise real energy consumption data for lots of buildings at the same time, but there are kind of ways of trying to normalise some of that data so you could still potentially use it in a kind of EPC type document. But yeah, it's difficult. Okay, thanks very much, Leslie, for that. And finally, we have Bo Han, also from Heriot-Watt University. And Bo's going to talk about using AAN technology to determine microclimate parameters for the National Library of Scotland's collections to enable energy efficiency improvements. Over to you, Bob.
Yeah, hello everyone. Yeah, my research topic is about using AI technology to determine microclimate parameter for National Library collections. And this project focuses on the storage room in National Library of Scotland. My presentation includes 4 parts: energy saving solution, research framework, experimental study for buffering effect of enclosure, packaging enclosure, and final part is about develop of heat mass transfer model. And first, I will introduce the situation of precision air conditioning in National Library of Scotland. In a whole year monitor data, we can see the accuracy of environment control is quite high. The fluctuation for whole year are smaller than 5 centigrade and 5% RH. As we know, some of HVAC components, such as chillers, have large time lag, so there are overshoot and undershoot in process control. To maintain a stable temperature and RH in room, we need to eliminate the overshoot and undershoot by the components with quick and accurate response, such as electric heater, humidifier. This process have to consume energy obviously, and how stable environment can be maintained depend on how real-time overshoot and undershoot can be eliminated. So higher accuracy of environmental control will consume more energy. Can we use another solution, a passive measure without energy consumption, to address the overshoot and undershoot? Yeah, the answer is yes, because the National Library's heritage collection are packaged inside a storage box for preventive conservation. The box can provide buffering effect to moderate the fluctuation from the room. Based on this logic, the energy used to eliminate overshoot and undershoot can be saved. But we need to study the buffering capacity for box in different room environment. For our research framework, we have found a potential way for energy saving in the precision air conditioning. To achieve this energy saving measure, we use hygrothermal chamber to simulate room temperature and RH fluctuation to assess the buffering capacity of box. Based on the quantitative results, we have proved the feasibility of this measure in the short-term room fluctuations. Furthermore, to describe heat, air, and moisture transfer between room and box, we developed a HEM simulation model based on a series of physical property tests. We use SEM to observe microstructure of material, use laser flash equipment to test thermal diffusivity and specific heat, and use the weight method to measure equilibrium moisture content curves and water vapor permeability, and use tracer gas concentration decay measure to test the air change rate of the box. Here, the tests about buffering effect and physical properties have been carried on in lab. And based on the test result, the HEM model was created and validated. In further, because we need a model with quick response for energy saving control, an AAN model will be trained and as the agent model of a HEM simulation. In the experimental study of box buffering capacity, this is the chamber. This is a chamber used to simulate the room temperature and RH fluctuations. There are 2 loggers to monitor room and box environment, and the study includes 2 parts: temperature buffering and humidity buffering. To quantify both buffering capacities, the room fluctuations are designed as harmonic fluctuation during different periods of time, and the temperature is increased or decreased decrease 5 centigrade in 10 minute to 90 minute durations when the humidity is fixed at 50% RH. Similarly, the RH is increased or decreased 10% RH in 10 minute to 3 minute durations when the temperature is fixed at 20 centigrade. Based on the data recorded by temperature and humidity loggers, we can find that box temperature and RH fluctuations are 1 to 2 centigrade and 2% to 8% RH smaller than that of room respectively. With the increase of fluctuation period, the difference between room and box fluctuations are decreased until their fluctuation period reach 90 minutes and 3 minutes. That means the heat and mass transfer between room and box reach a steady state. The heat and mass exchange across both is in equilibrium. In the HEM simulation model, heat transfer depends on moisture balance, and the moisture balance also affects the heat transfer. Temperature and moisture content can affect the air density and permeability of the porous media, and in turn, the mechanics of convective heat and moisture transfer affect temperature and moisture content. In the heat balance equations, the thermal storage and transport properties of the air depend on the moisture status. The temperature field affects the moisture transfer property since the temperature gradient is one of the driving force for the moisture. Meanwhile, vapor permeability, moisture transfer coefficient, and stated vapor pressure are temperature dependent in the moisture balance equation. And for our case, because the air exchange rate between room and box and hygrothermal behavior of the material affect the process of heat, air, and moisture transfer, we carry out following tests to provide actual data for modeling. And the microstructure of box in vapor is porous. The thermal diffusivity is about 0.08, specific heat is about 1, and conductivity is about 0.05. The equilibrium moisture content curve will obtain to reflect how much moisture can be absorbed or released in different temperature and RH conditions. Also, water vapor permeability and diffusivity were tested. Finally, the air exchange rate is about 19 air change per hour. Although this value is higher than ACR of the stored case too much, but to consider the general storage of heritage collection without any sensor to measure the micro environment inside the box, and the of gas product generated by the collection should be exhausted from the box to the room based on an appropriate ACR, air change rate. And finally, to achieve quick and accurate control in practical, we need to train a model based on the result of a HEM simulation. When we input room temperature, a series of time series room temperature and RH in the AM model, corresponding box situations with output. If of the box situation comply with the environmental standard of preventive conservation, the relaxing accuracy of environmental control will be acceptable. Otherwise, we need to improve the design accuracy until finding an optimal control accuracy for room temperature and RH for energy saving. In further, we also need to develop a model to simulate energy consumption and accuracy of room environment control for the study of control strategy. Yeah, thank you.
And for the final time, any questions?
So will this reduce energy consumption in the library?
Yes, yeah. The storage room of, in a National Library, because in this kind of case is little bit different with comfort air conditioning, because they focus on accuracy control. For example, for daily control, they setting a control band for temperature 15 to 20 centigrade, and for IH 50% to 60%. Also, they have requirement for fluctuation, daily fluctuation. Every day, the maximum fluctuation must be smaller than 3 or 5 centigrade, depending on which kind of collection they store. And for RH, also 10% or 5% RH. So if we want to maintain a very stable and very small fluctuation, temperature and RH fluctuation in room, we have to use the precision air condition. And the to eliminating overshoot and undershoot is the most important part to maintaining. Yeah, actually, this is my research, because we use the paper-based box to package the heritage collection inside. The box can provide buffering capacity for temperature edge fluctuation. This our idea. We just focused on the micro environment inside box, not whole room. Yeah.
Other questions on the floor? Quick question for me. So you've done a bit of experimental work and some of the modelling work. What's your plans next? Do you feel you need to do more experimental work, or do you just want to work on the modelling side and expand that? What's the next steps?
Yeah, next step actually, we have to combine the hand model, AM model. Actually, AM model is an agent of hand model. Yeah, the AM model can predict the temperature and RH inside the box, and based on this model, we also need to create energy consumption model for the precision air conditioning system. Combine these two, we have to design a control logic to search optimal control accuracy for the room. Yeah, because the energy consumption depends on control accuracy.
Mm-hmm. Okay, so that will require a little bit more experimental work to feed that that model.
Yes.
Yeah. Okay, that's interesting. Okay, unless I see any other questions, then thank you very much, Bo, for that presentation.